All right, so we're continuing on, but just remember that these are marked red because we submitted the first answers without checking or doing the rest of them. So this one's a little bit tricky to take a look at, but the key is to, again, look at that denominator and look at the parentheses. Usually if something's in parentheses, that's a good idea to make u. And if I do that, I'm going to have u equals 5 plus x to the 1 over 9. And what does that derive to? Well, 5 derives to 0. The 1/9 will pop down, and I'll have x to the negative 8/9 when I carefully subtract 1 from 1/9. Now, x to the negative 8/9 is otherwise known as x to the 8/9 on the bottom. So in other words, this is what I have in my integral. What I don't have is I don't have a 1/9, so I must have a 9 multiplying to both sides. So in other words, 9 du is what I have in this fraction. I've got x to the 8/9 in the denominator and a dx multiplying out front. Great. So it turns out that this whole thing is just the integral of 9 du over u, which is once again ln. So ln absolute value of something plus c, and put in the original x. So 9 ln absolute value 5 plus x to the 1 over 9. Let's see if that typed in correctly. Perfect. And don't forget the plus c. Great. All right, now this next one is a real tricky one. How are we going to integrate secant? Now, I'm just going to kind of give this to you and let you marvel at the fact that someone figured this out. But let's just first figure out, let's just verify it backwards, so to speak. So it turns out that if you have the natural log of tangent x plus secant x, and you derive it, something very special happens. So let's derive this. Well, tangent derives to secant squared, and secant derives to secant times tangent. And well, we're deriving ln, so we just derived the inside, and it's time to put it over the original inside. All right. There's one very clever trick that happens here. Notice your numerator has a common secant, which we could factor out. So now we have secant times secant plus tangent in the numerator, and my denominator is, well, tangent plus secant. And, well, because addition can be done in any order, these two cancel out. So it turns out that secant integrates to ln of tangent plus secant. That is a crazy fact, and how someone figured that out probably took a lot of trial and error. So this is the big crux to the problem, is just memorizing that that's where secant comes from if secant is your derivative. So it's not a derivative rule we've seen before, it's a new kind of result, so to speak. Secant as a derivative comes from this. Now we also have a u substitution to deal with, so first u equals x over 9, which means du is just 1 over 9 dx, but I don't see a 1 over 9 in my problem, so this must be 9u. So now we have 9 integral of secant u du, and of course that's 9 ln absolute value tangent u, but u is x over 9, plus secant u, but secant is x over 9, plus c. All right, so there would be your answer. All right, it is that point of the night where I am going to start getting lazy and not type these in. Oh gosh, you know what? No, I said it, and I just have to. Something in me is compelled. 9 ln tangent of x over 9 plus secant of x over 9, and don't forget the plus c on the outside. All right, up next, another indefinite integral. We've got another trig one. Now this one is, again, a little bit new, a little bit different, but we can actually kind of arrive at this a little more simply. So what we're first going to narrow in on is, where does tangent come from? And we're going to remind ourselves that, well, tangent is a fraction. Tangent is sine of x over cosine of x, dx. And in other words, hey, cosine derives to a form of sine. If u is cosine, then du is negative sine. And, well, I don't see a negative here, so the negative must have multiplied to the other side. So it turns out that this is going to be negative ln absolute value cosine x. Interesting. All right. Because, again, we have a original and a derivative of it on top, although there is that extra negative that's kind of lagging or disappeared somehow. All right. So with that new derivative rule, let's get through this next problem. Notice we're also integrating with respect to theta, so I will need 9 theta. Usually you can just type in theta and it will turn into that as you go. Awesome. And now the idea is I also have a little bit of a u sub problem going on here, but that over 4 just means I'm going to have a 4 pop out. Also, notice that I'm going to exploit a few more fun tricks here as I speed up my homework, but really write all this out by hand. You don't want to risk memorizing this, but what I'm noticing is that when I integrated positive tangent, I had a negative pop out. So I'm betting that when I integrate negative tangent, I'm going to have another negative pop out, and it will then become positive. So I'm going to have 4 ln absolute value cosine of, and then I'm going to have my theta over 4. And uh-oh, I needed absolute values around all that. Cosine of theta over 4 plus c. All right, now that one I'm just feeling a little bit risky on, so I think I'm going to check those right now, and then we'll continue. All right. Awesome, we're doing good so far. Okay, up next, this one becomes a little bit more obvious, so I actually think I'm going to skip this one because, hey, look, 9 plus sine of t, that just derives to cosine. There it is in the numerator. Just be careful to use t's. So let's move on to this next one. It's another integrating tangent question. So, again, we're going to be really careful here. So, when I integrate tangent, this is also like a u sub question. So the first thing is we're going to say, well, let's simplify the inside of tangent. So let's say that u is equal to e to the negative 9x, which means du must be negative 9 e to the negative 9x dx. So there we go. But again, there's no negative 9 out front, so we should probably divide that out. Great. So what do we have now? We have negative 1/9 integral of, let's see here, e to the negative 9x dx is all collectively that negative 1/9 du. And I now have tangent u left over. And what we saw before was, well, tangent comes from the negative ln of cosine of u, and u is e to the negative 9x plus c, and we're going to deal with that double negative. So 1 over 9 ln absolute value cosine e to the negative 9x, and don't forget the plus c. All right, the last few are definite integrals. So we're just going to actually evaluate this thing, and maybe we'll see why the absolute values actually matter. What I'm going to do for this first one, it does go back to basic polynomials, so I'm going to already jump right to, I've done my u sub, I've dealt with the fact that a 5 is going to pop out, and I've got the absolute value, or ln of absolute value, 5x plus 1, and I don't need a plus c because I have an a and b. That's kind of the silly rhyme I've used so far. So, I mean, again, I'm going to double check myself. So I'm going to have a 2/5. I'm then going to have a 5 multiplied to the numerator, which will cancel with those. And then I would have a 1 over that original content. So it would be 2 over 5x plus 1. So yes, I have got the derivative right, but it's time to evaluate this. So what do I get? Well, I'm going to have that 2/5, and I'll just let that multiply to whatever I get from both terms later. When I plug in 6, that's going to be ln of 31. Now I don't need absolute values because I already verified that that is positive. And when I plug in 0, I get, well, minus ln of 1, because 5 times 0 is 0, but there's still a plus 1. We'll just be careful about that because ln of 1 says e to what power gives you 1, and, well, any number to the 0 power gives you 1. So this is really 2/5 ln 31, because this whole thing is 0. The exponent of e that gives you 1 is 0, so this will disappear. All right, so 2/5, oops, and it looks like maybe they want me to verify my result, round my answer to 3 decimal places, so let me type that in. 2/5 ln of 31 to 3 decimal places looks like, oops, 1.374. All right, and we'll keep on moving. All right, this one is definitely a little bit interesting. I mean, it looks like I'm dealing with U substitution here. It looks like this might not actually be ln, it just looks like ln's in the problem, but we'll see. It looks like what's happening here is that u is 3 plus ln x, or in other words, I notice that there's more complex algebra with like a power rule happening to it, so maybe this is the u. And I get 1 over x dx, and again, in a way, that's what my problem has. There is a 1 over x multiplying to everything else, and a dx. So this is u sub, and it's actually fairly direct u sub. This is actually just u cubed du. And what I'm going to do is adjust those bounds right now. So if I plug in 1, the x bound into this, I would get 3 plus ln of 1. We've just discussed that ln of 1 is 0, so my new lower bound is 3. So I plugged in 1, and this evaluated to 3. So when x is 1, u is 3. What about when x is e? Well, ln of e is 1, so I now have 3 plus 1. So again, when x is e, u evaluates to 4. Awesome, I've got my new bounds, and I'm going to finish integrating. I've got u to the 4th over u, evaluated at 4 and 3. Well, that's going to be 4 to the 4th over 4, and so I'm just going to notice that I'm going to have some cancellation there. Minus, and I don't get lucky this time, 3 to the 4th over 3. And I think they want me to round that. No, they just want to get a precise answer. Interesting. I guess I'll just type that in. 64 minus, whoops, that's not over, that's over 4. 64 minus 81 over 4 is 43.75. All right, and we've got one last question, which is actually just an allusion to the fundamental theorem of calculus. And remember that f is an integral. So f itself is an integral expression. And so when I derive an integral, I'm essentially going to have nothing, quote unquote, happen. So I'm going to end up with 9 divided by that bound, that algebraic bound substituted into, or in place of t. But I also get something extra this time. I get a derivative of the upper bound. I always get a derivative of the upper bound multiplying. Maybe I'll put that into the numerator, 18x. But the idea is the reason that we see it this time is because, well, that isn't just a simple x. It's x squared, which derives to 2x. And the reason this happens, again, has to do with the chain rule. We went over that before. You could watch a video on this. We call this the fundamental theorem of calculus with the chain rule. Let's check all the rest of our examples. We skipped over that one. Got that one, got that one, got that one. Awesome. Well, there is 5.7. Happy studying. Hopefully seeing me work these out helps you along the way.